This is our project of investigating diffusion, in which we changed the type of solution the constant-sized beads moved through. Using water, dish soap, and corn syrup, we predicted that the rate of diffusion would be fastest in water and slowest in corn syrup due to density. Throughout all of our microscope videos, we recorded the upper layer of beads that were moving and saw that the beads mainly moved in an oscillating motion together in one direction. Therefore, the beads' movement appeared as coherent motion instead of random motion. However, since random motion takes place in 3 dimensions, the limitation of the AmScope recording from top down could have prevented us from viewing the full random movement.
Particle diffusion is dependent on factors including the mass and size, initial velocities, concentration of the particle, and the container size. As mass increases, diffusion slows. Initial velocities that are high are associated with higher initial diffusion rates. Higher concentrations diffuse down the gradient more quickly than solutions of similar concentrations. Container size will constrain motion and change how much distance particles must move to diffuse. Physics models we considered was Fick's law, which can be defined as an object in high concentration will move to an area with low concentration. Therefore, the net flow of molecules is due to concentration, not due to preferential directional movement. Other words to define in this video is diffusion, random motion, and coherent motion. Diffusion is the movement of particles from high to low concentrations. Coherent motion is defined as a set of particles moving in the same direction. Random motion is the motion of particles with no controlled direction of movement. With this type of motion, eventually the motion will spread evenly throughout the medium. Our controlled variable for this experiment was the size of the bead. The variables that we changed was the solution the beads were in. In this experiment, we used water, corn syrup, and dish soap. Our procedure for the experiment went as follows. Place the dropper with solution on the slide, focus the lens on the beads at the top of the solution, then record the slide. We then uploaded the video to Tracker for analysis in order to measure the bead's velocity.
Here are the videos for dish soap and corn syrup solutions. Our videos for the water were unable to be used since the fact the beads moved too quickly for Tracker to analyze the velocity. The following graph shows the velocity of the 2 micron beads over approximately 14 seconds for both corn syrup and dish soap. Since the beads moved relatively straight, the x-axis was rotated so that the x-axis direction velocity is the most significant velocity component, while the y-axis velocity component is negligible. It's obvious that the beads in the soap has significantly higher velocity as indicated by the red line. This is because the beads diffuse more quickly in the dish soap. Velocity is not reported for the beads in water since the microscope frame rate was too slow to accurately capture the beads' velocity in water.
The computational simulation of random movement was an ideal situation in which all of the molecules diffused in different directions. This is because eventually all of the particles spread out evenly throughout the inside of the cube until they reached an equilibrium state. The particles are also moving in a random direction with a random starting velocity determined by the code's programming. In our experiment, the beads appeared to be moving coherently, unlike the code. Our beads never reached a true equilibrium state due to the force of gravity causing them to settle at the bottom of the given solution. This force of gravity, in addition to the 2D method of video recording, both limited our capability to observe ideal random motion. As previously stated, there were several pieces of evidence that suggest reasons why we didn't observe clear random motion, such as the 2D camera. The densities of the solutions are stated here, increasing from water, dish soap, to corn syrup, with the largest density. Our average velocities listed were inversely related to these densities as we hypothesized. Water average velocity could not be calculated because the beads left the AmScope camera frame too quickly for us to track the velocity over time. However, the water solution's fastest velocity matches the pattern of data. Overall, we met our goal for exploring the different solutions' impacts on diffusion.
There were several sources of error we acknowledged. The most significant error is the lack of reported velocity for the beads in water due to the frame rate being too low for Tracker to track the beads. Other minor sources of error include the microscope lens could only focus on a particular layer of the beads, so care to be taken to avoid already settled beads, as well as any bumps or air movement would cause the beads to resettle. Bubbles were common with the soap solution and easily mistaken for microbeads.